Good morning, everyone. My name is Jaemin Shin. Today, I'd like to discuss a methodology to integrate multiple vision platforms on construction site through a unified 3D map. Various vision platforms are being utilized to manage the construction site using their own strengths. For example, Terrestrial Laser Scanner, or in short TLS, can generate a high precision model of the structures. And UAV can produce rapid and wide view of the site, uh, making it ideal for site mapping. And CCTV can continuously capture the time series data. However, they also have their inherent drawbacks. TLS is slow and require manual operation, so it making it impractical for large-scale site mapping. And UAV is usually deployed in high altitude, so they have low spatial resolution and miss vertical details. And CCTV has limited field of view and is prone to tracking error, especially in complex scene. To compensate for each other, we propose to integrate these vision platforms into unified 3D map. UAV can generate the overall 3D map, and TLS refine the key structure with their high precision model. And CCTV track the moving objects and give the dynamic information into 3D map for robust object tracking. To integrate UAV and TLS map, ISP is a good option. ISP method is a popular method for fine registration between different point clouds. However, it requires a good initial alignment. So in this paper, we implement the initial alignment with GPS. And another challenge is large-scale registration. As you can see below, UAV and TLS map represent the same structure, but they have very different point distributional characteristics. It is important to carefully deal with this difference for accurate registration. Moreover, we should consider the high computational cost in large-scale scene like construction sites. And there are two main existing methods for camera-based 3D object tracking. Because their performance is very rely on the complexity of the site. We should develop a new and robust object tracking method. To summarize, various vision platforms on construction site have their own strengths, but also inherent limitations. Because these platforms are used in isolation, the full potential of visual data is very restricted. So in this paper, we propose a framework that combines diverse vision platforms on construction sites through a unified 3D map to compensate for each other. The methodology consists of 3 steps. Step 1 is overall 3D map reconstruction. 2D aerial images captured from UAV are processed to generate an overall 3D map. And step 2 is map refinement with registration. Vertical objects like wall are scanned with TLS, and this TLS-based point cloud are then aligned with UAV map to refine the key structure. And step 3 is object tracking in 3D map. Moving objects like worker and vehicles are tracked using CCTV footage. These 2D object tracking results are then back projected into 3D map to give the dynamic information into the map. In concrete, 3D map reconstruction step it starts with UAV deployment to capture the aerial image of the site. And next, matched points across image sequence are found to reconstruct the 3D geometry. And next, we apply the multi-view stereo to densify the 3D map. And this is for step 2. We start with GPS-based coordinate alignment to roughly match the UAV and TLS map. After that, we apply hierarchical registration. Both UAV and TLS map are downsampled to reduce the computational cost and mitigate distributional variations. After that, we apply FPFH for coarse and global registration. And this step makes a very good initial alignment. So we apply ICP for further fine registration. And this is for step 3. We start with camera calibration to estimate the projection matrix P, which maps 3D world point to 2D pixel point. Then 2D tracking results is back projected to 3D map with ray marching method. Because object tracking is not very robust, we further apply the multi-view fusion. For example, as highlighted in green, object 1 first appears in camera 1 and is registered into 3D map. And after that, as highlighted in orange, the same object 1 appears in other camera and the system starts track matching. Track matching compares with the existing position in 3D map and choose the point with lower error. This can handle the duplicate among the multi-cameras. A site in Seoul National University is chosen as test bed, and on the right figure, it shows the test bed with reference lanes is built for verifying object tracking. Experiment 1 is for map refinement performance. As you can see on the left side, initial 3D map meets the vertical plane of the building and and lack of the details in structure. But our proposed refined 3D map successfully recovered the vertical plane and refined the details in structure. And table on the right shows that our proposed method outperformed the baselines and maintained the practical runtime. And experiment 2 shows that the object tracking performance. As you can see on the left, our proposed ray sampling based method outperforms the other 3D object tracking method. And ablation studies show that with multi-view fusion, we can handle the duplicate among the cameras and interpolate track failure, enhancing the reliability of object tracking. To summarize, we successfully proposed a framework that combines diverse vision platforms on construction sites through a unified 3D map. And here's our contributions. First, we enhanced the utility of digital maps for digital twin. And second, we developed a outperforming online method for UAV and TLS map. And third, we implemented a robust 3D object tracking with spatial context. Here's some directions for future work. And this is my contact detail. Thank you for listening my presentation.